Okay, we'll get started today. I hope everyone is doing well. And so we've covered confidence intervals, and we spent some time going over the interpretations and the understandings of what the confidence interval means. And we will continue on in our section on statistical inference. And today the topic will be hypothesis tests. And with hypothesis tests, we are testing what we might consider a belief or a hypothesis about the population. Okay, so we begin with some kind of belief or hypothesis about the population. Okay, that we wish to test. And then we look at some data, and we see if the data kind of contradicts this belief or hypothesis. Okay, we'll look at some data, and then we see if the data and the hypothesis contradict. Contradict each other, okay? And so if there is a contradiction, then the fact that you have this data then causes you to doubt or reject this belief or hypothesis. I'll say if there is a conflict, then the fact that this data exists causes us to, doubt or reject our hypothesis or belief. Okay. On the other hand, if there is no conflict between the data and the hypothesis, if there's no conflict between the data and hypothesis, then we go about continuing to believe our hypothesis or belief. Okay. It does not prove that our hypothesis is true, but right now we have no reason to question it. Okay? Okay, and this is kind of a little bit of the framework in which we're going to work. Okay, so we set up some hypotheses, we look at the data, and we see if there's a conflict. Okay, and the way we measure is there conflict or not is we ask. Okay, so this is the way we measure if there's conflict. Conflict between our data and belief, or between the data and hypothesis, okay, the way we do this is we calculate the probability of observing our data if the hypothesis were assumed to be true. Okay, and this will all make sense. I know it's kind of a lot to take in right now. Okay. We calculate something called a p-value, which is the probability of observing our data or something more extreme if the hypothesis is true. Okay. So here's just a bunch of text for you guys to write down or copy down into your notes, and then we'll do kind of we'll do an example to kind of work with these concepts here. Okay, can I flip to the next slide here? Yeah? Okay, here we go. Okay, so imagine, I don't know, you meet a person, okay, and for whatever, this is not recommended life advice, but let's say you meet someone and you decide, oh, you know what, let's start gambling against each other, okay? So you meet someone and then you decide, okay, let's start to gamble. Okay, meet a person, and then you start to gamble. All right, and the game is very simple. Okay, the easiest, simplest game. Okay, the game is flip a coin. Okay, and if the coin lands heads, you win. And if the coin lands tails, let's give this person a name. What should we call this person? We'll say Tom. Okay. Tom wins. Okay. So if the coin lands heads, you win, and if the coin lands tails, we'll say Tom wins. Okay, and Tom insists that he flips the coin. Okay, well, it's a little strange, but sure, we'll go with it. Okay, so Tom does the coin flipping. Okay, so let's say you play 10 games. Okay, you play 10 games, and let's say it lands heads 7 times and tails 3 times. Okay. At this point, do you think Tom is cheating? Okay, and what do you think? The answer is no, of course not, right? If anything, he's giving himself a disadvantage. He's like he doesn't understand how cheating should be working, right? Do you think Tom is cheating? And the answer is no. If anything, we came out ahead. There's no reason to think that Tom is cheating at this point, right? We came out ahead. We have no reason to think he is cheating. Okay, let's have another scenario. Okay, you play 10 games. Okay. And this time it lands heads 3 times. And tails 7 times. Okay. So what do you think? Do you think Tom is cheating here? What's that?
So maybe he deflated the coin.
He deflated the coin? Yeah, that's certainly. And then he'll go on to have an amazing second half of the Super Bowl, right? So, okay. So if we play 10 games and it landed heads 3 times and tails 7 times, do you think Tom is cheating in this case? What do you guys think? Maybe, maybe not, right? So you ask Tom, "Are you cheating?" And what does Tom say? Right? He says, "No, I'm not cheating." Right? So you can imagine this conversation, right? Tom, are you cheating? Are you cheating at the game? Okay. Anytime somebody asks you, "Are you cheating?" Well, maybe not you, but Tom's going to say, "No, I'm not cheating." Okay? What are you talking about? Okay? What's Tom's defense here? Tom says, "No, I'm not cheating. That's just what happened to the coin, right? I just got a little bit lucky. I won a couple times, right? I just got a little lucky." Okay. And is that possible? Yeah. Yeah, if we flip a coin, if somebody is not playing a game and they flip a coin 10 times, it's very possible for the coin to land heads 7 times out of 10, right? That could happen. Okay? So, okay, that's possible, right? So what we say is that, if a person flips a fair coin 10 times, it is very possible to get 7 heads or 7 tails. Okay. And so at this point in time, we don't have any reason to believe that Tom is cheating. Okay. It doesn't prove that Tom is innocent, but it doesn't prove that Tom is cheating either. Okay. So because this is quite a real possibility. Okay. Because this outcome is quite possible from random chance, we can't conclusively say that Tom is cheating, okay? Because the results could have happened from random chance. We cannot say that Tom is cheating. Okay. Is it possible that he is cheating though? Yeah, it's possible. Okay, and that could be why he won 7 times out of 10. Okay, but it could also be that he won 7 times out of 10 just from random luck too. Okay, so right now we can't tell. We can't tell if it's just random luck or if there's cheating going on. Because either case is possible. All right. So far, so good. This line of thinking. Okay. All right. Now, let's say you play 1,000 games. Okay. You're like, well, that was fun. Okay, let's play 1,000 games. Because, again, not a advised strategy here, but so you play 1,000 games, and this time it lands heads only 300 times, and it lands tails 700 times. Okay. Now, do you think Tom is cheating now? Yes. Okay. Right. So we say, is Tom cheating? We feel pretty strongly that he is. Now, why is that the case? Okay. So again, we go to Tom and we say, Tom, are you cheating? Tom, are you cheating at this game? Are you cheating? Okay. And what does Tom say? Tom says, no, I'm not cheating. Okay. I just got lucky with the coin flips. Okay. Same defense. Okay. Now, is that possible? Is it possible that Tom just got lucky with the coin flips? That he got 700 heads out of 1,000 coin flips? Or 700 tails out of 1,000 coin flips? Technically, it's possible, right? It's possible. All right. Okay. Okay, so technically, this is possible. It's not impossible. It is technically possible. But we're going to say, okay, well, just for argument's sake, let's say I believe you, okay? Now we're going to do some calculations, and we're going to say, well, what is the probability that you get this lucky, right? So we say, all right, let's say I believe you. I don't really, but let's say I believe you, Tom. Okay, we're going to say, what is the probability that a coin flipped 1,000 times will land tails 700 times, and then and we would say or more. Okay, and the reason why we would say or more is because if we accuse Tom of cheating when he got 700 tails, we would also accuse him of cheating if he got 701 tails or 702 tails or anything more than 700 tails, right? So we're going to include all of those things wrapped up in here. Okay. So we're going to ask, what's the probability that, you know, a fair coin flipped 1,000 times will land tails 700 times or more? Okay. Do we know how to answer this question? We do. This is a sampling distribution problem, right? Over here, we're basically asking, you know, so this can be written as, framed as a sampling distribution problem. Okay, we're going to say that the probability that the coin lands heads is 0.5. We're going to take 1,000 coin flips, and our p hat is 0.7. We want to know, okay, if we we're expecting it to be around 0.5, what's the probability that we get 0.7 or more? This is what we want to know. Okay, so we'll do some calculations here. Okay, so we start off with what? We get our calculate our standard error, and we do p 0.5 times 1 minus 0.5 divided by 1,000, and I get a standard error of, I think, like 2%. I don't know. Let's figure this out. Square root of 0.5 times 1 minus 0.5 divided by 1,000, 0.015811. Okay. Okay, so this is my standard error. And then my z-score is going to be 0.7 minus 0.5 divided by 0.015811. Okay, so I come over here and I do 0.7 minus 0.5, and we're going to divide by this. Okay, and what do I get? I get a z-score of 12.65. Okay. All right, so what did we say was the guidelines for z-scores? We said if it's bigger than 2, it's unusual, and if it's bigger than 3, it's highly unusual. And here we are at 12.65. Okay, so this is absurdly unusual. Okay, this is like ridiculous. Okay, this is a ridiculous z-score. All right, the z-scores over 3 are considered highly unusual, and here we are at 12.65. And I actually, I lost that number. Let me do the calculation here. I think it's on the order, I want to say 5 times 10 to the negative 37. Let me just do p norm negative 12.65. Yeah, 5.6 times 10 to the negative 37. Okay. Okay, I don't. So this area out here is 5.6 times 10 to the negative 37. Now, it's hard to comprehend a number that small, but basically we're going to have 0, 0, 0, 0, dot, 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 0, 0, 0, 0, 0, 0, 0. Okay, there's 36 zeros here, and then we have a 5, 6. Okay, this is approximately the probability of hitting Powerball 4 weeks in a row. About, okay. Okay, so, I mean, is it technically possible for the same person to win Powerball 4 weeks in a row, you go to the gas station, you buy a lotto ticket, you win, okay? And then you go the next week, and then you win again, and then you win 4 weeks in a row. Is that technically possible? Technically, it's possible, right? But will that ever happen? No, right? Like, there's going to be, like, after the second win, they would open up an investigation, and then after the third win, they would shut down the lottery, and it's not going to happen, right? So our friend Tom is saying, no, I just got lucky. I got 700 heads out of 1,000, or 700 tails out of 1,000 coin flips, and so I mean, technically it is possible, but it is so incredibly unlikely that we're not going to believe Tom, okay? So 700 tails out of 1,000 flips. Okay, this is our data, all right? So it is technically possible to get this data if the game is played fairly. However, the probability of this happening is so negligibly small. It's so small that, you know, we conclude that Tom is not playing the game fairly. Okay. And so this brings us to kind of our first, I guess, set of decision rules for how hypothesis testing will work, okay? Okay. What we do is we calculate the p-value, which is the probability of our data if the null hypothesis is true. Okay, so we find our p-value. Probability of our data, or something more extreme. If the null hypothesis is true. And then, if the p-value is small, okay, like in our case here, where we found the probability of getting our data was really small, if that p-value is small, we conclude that our hypothesis was wrong. We conclude that the kind of the initial belief must be wrong. So So after, you know, in our case we said our null hypothesis, our initial belief is that Tom is playing the game fairly. You know, because the probability of getting our data was so small, we came to the conclusion that that initial belief is wrong. Okay? And on the other hand, if the p-value is large, okay, we will not reject the null hypothesis. And that was kind of the flip side, where after only 10 games, sure, Tom came out ahead, but because we said it's also quite possible for this data to have happened from random chance, meaning that the probability of observing this data is high, where we can't reject the idea that Tom might be actually playing fairly. All right, so let's try an example out here. And we'll see, you know, can we, well, okay, so let's talk about how we go about doing hypothesis testing. So that's kind of the overview framework, and there are a few parts to a hypothesis test. And so today we'll just start off with step one, which is creating our hypotheses. Okay, step one, we'll talk about the hypotheses. All right, and so as far as the hypotheses go, okay, we have a null hypothesis, okay, which we write as H0. And the null hypothesis is always going to be P is equal, and it's some number, okay? I'm going to put like P0 here, okay? But, you know, the example could be that the null hypothesis is that P is equal to 0.5, or P is equal to 0.2, okay? It's P is equal to some proportion, P0, okay? One thing to note is that the null hypothesis always has an equal sign. Okay? And we write our null hypothesis almost with the hope of eventually rejecting it, okay? Almost hoping to reject it, okay? It's the equal sign here that makes it a testable hypothesis. Okay? And then the other hand, we have the alternative hypothesis. Okay? The alternative hypothesis is that P is either not equal to whatever that number is, or P is greater than that number, or P is less than that number. Okay, so it could be, you know, P does not equal 0.5, or P is greater than 0.5, or P is less than 0.5. So we might say that the alternative hypothesis is always identical to the null hypothesis, except the equal sign is replaced with something else. And whether we choose a greater than or less than or not equal sign depends on the question, okay? The choice of not equal or greater or less depends on the question. Okay, so I guess we're gonna run out of time. We'll do our first clicker question here. Okay, and so let's say I don't know, some advertiser claims that, I don't know, 4 out of 5 experts recommend product ABC. Okay, and you're like some consumer watchdog group, right? Okay, so you want to test that claim. You want to test that claim and see if the actual proportion is lower than what the advertisers claim. Okay, so what should your hypotheses be? Okay, so we'll have A, B, C, and D. Let me start up the clicker software. Okay, so we'll have a null and an alternative, and I got to just kind of make up some choices here. Start a new session here. Okay, so we'll say P is equal to 0.8. P is not 0.8. P is equal less than 0.8. Say P. Okay, so I hope, I think this is working. Okay, go ahead and oh, okay. All right, everybody responded. Okay, is this everybody? That was quick. All right, I'm gonna hit stop, and let's see guys what you picked, and that is correct. Okay, so yes, this is the answer. Okay, so the advertisers are claiming that 4 out of 5 recommend product ABC, and you want to test the claim and see if the actual proportion is lower. So that's how we decide that the alternative is going to be p is less than 0.8, okay? The null hypothesis always has an equal sign, so that eliminates choice C and D, okay? And so it's going to be the equals 0.8 versus less than that, all right? So the null hypothesis always has an equal sign. Okay, so so you read the problem, you set up your hypotheses, okay? And the second part, and I guess this is as far as we'll get today, step 2, we call this kind of our preparation step. Okay, and in this step we check the conditions. To use the central limit theorem, okay? And this is, you know, your random and independent condition, the large sample condition, and the big population condition, right? So you check these things. Now, for exams, it's hard to write questions where you're supposed to check these things, because if these conditions fail, you cannot continue the analysis, right? Okay, and so for quizzes and exams, it's really hard to write questions where you're supposed to do this step and then have like more questions that kind of are related to the analysis without this part feeling like a trap, okay? Because you know, if it's like, oh, you know, what was the p-value? Oh, just kidding. You were not supposed to find a p-value because the conditions failed. I feel like I'm writing trick questions there. So the way I'll handle this is, for the questions where you do analysis, you can assume the conditions are met, okay? And I'll have separate questions where you check the conditions, kind of like on the midterm you had separate questions for checking the conditions. It'll be kind of like that, all right? Checking the conditions is an important thing that we do in statistics, but as far as questions where you do analysis, you can assume that the conditions are met, okay? And then the other part of this is we select something called, also select a significance level, which we call alpha. Significance level called alpha, okay? And the default, if alpha is not specified in the problem, assume that it is 5%. Okay, and I guess we'll stop here, and we'll talk about I guess the rest of the hypothesis testing process here. Okay, we'll see you guys.